Good day. Welcome to part 13 of our C tutorial series. In this part we're going to look at structures, or structs. Structures are kind of like the objects of C++ or Java, in that they allow you to aggregate variables together into a coherent form that makes it easier to reason about your program, and also just easier and less troublesome to pass around lots of variables, because you can group them together and pass the structure around instead. So to give an example of that, imagine that we're writing a program to manipulate some kind of graphics system, and we've got a pixel. And a pixel consists of red, green and blue components. If we use if we assume an 8-bit RGB color space, so that red has 8 bits, green has 8 bits and blue has 8 bits, then we need 3 bytes to store it. Now what we could do, of course, is we could use something like an unsigned char, and we could say R, G and B, and we could declare these variables, and then we could pass these variables around. And then every function prototype would have to have something like, I don't know, let's say it was set background or something, so set BG. You'd then have to have unsigned char R, unsigned char G, unsigned char B in your function prototype, and then have your function definition down there. And for 3 variables that's not too bad, but imagine you've got some other kind of structure or some other kind of conceptual object, a semantic object. A book object for a library might have an ISBN, have a title, have a some kind of sorting code, might have a price, an online shop. You'd have all these different things, fields, descriptions and all this kind of stuff. And you wouldn't want to, every time you manipulate that kind of semantic level object, you wouldn't want to pass all of these variables in continuously, especially when you might end up with hundreds of variables. If you're representing something very complicated, like imagine you're writing a computer game or some kind of simulator. Yeah, simulator is a good example. So I wrote a simulator for cellular networks, and you really wouldn't want to represent all of the parameters of the base station outside of the context of some kind of semantic encapsulation. I mean, imagine every time you wanted to manipulate the base station, you had to pass in the angle of the sectors, the transmission power, the height above the ground, the antenna pattern, and like all of these things. And if you had to pass them as separate parameters, it would be kind of bonkers, rather than just passing a kind of encapsulated base station structure or base station object. So encapsulation is the goal here, and it reduces the semantic and it reduces the cognitive burden on the programmer, and it makes things more understandable. So in order to declare a structure, which is our encapsulating mechanism, we do struct and then the name that we want to give the struct. So say we had pixel, then we do a curly brace. Oh, that looks terrible. We do a curly brace, and then we just declare all of the variables that we want to encapsulate within our pixel or within our structure. So we'd have unsigned char R, and then we put a semicolon. So after each variable we put a semicolon. Unsigned char B. Sorry, it's normally RGB, isn't it? Not RBG, doesn't really matter, but unsigned char B. And once we've done that, once we've written all the variables we want to encapsulate in there, we then close off the brace and we put a semicolon. now our structure pixel is declared. What we can then do is we can use that as a variable. So, and to do that we can say struct pixel p. Now p is a variable that has been declared with this new type that we've created essentially. Essentially we've created a new type called struct pixel p. And we can then set the values associated with our pixel p by using dot notation. So we'd say p dot r equals 0, p dot g equals 255. So let's say this is just a green pixel. P dot b equals 0. So we can then, this will then set those values on our struct pixel type p. What we can then do is we can write that in our function prototype as well. So we could then write, what was it, set background? So void set bg, and we just say struct pixel p. And now we're just passing the struct pixel type into our function. And then we can just use that within the function, and we can reference the objects, or reference the variables within that struct by using our dot notation again. And so we're kind of encapsulating then the values that passed in. So just to note here that when you declare a structure, the structure variable, so when we had our struct pixel p, that will declare the space for those 3 unsigned characters in memory on the stack in this case, and they will be contiguous in memory. And when we pass that into a function, we are making a copy of the whole structure. So this is a copy of the entire structure, because remember C is always passed by value, which means that if we modify P within this structure, within this function, like if we passed it in here for example, then at this point, even if we modify P inside the function, P is not going to have changed because we're passing in a copy. If we want to modify the actual structure, then we need a pointer to it. Now, kind of at this point, what I want to do is, I never use structures like this. I always what's called typedef them. So you can typedef a structure and you can give it a new, essentially you create a new type name for the structure. And the advantage of this is you don't have to keep writing the word struct over and over again, because if you notice, essentially our type here is struct pixel, and we have to keep writing struct pixel everywhere, and it can become very confusing if you have pointers to structs and so on. I always typedef my structs, and the way to do that, and the easiest way to do that, and the best way really to just go ahead and get on with using structs is just to typedef them. So you would then say type, if I can if I can write, you would say typedef, so to define a new type, and this is a general thing you can use, and the syntax is typedef, then the type that you're trying to define or give a name to, and then the name. So you can, for example, just to show you, we could say typedef int resolution or something. If we wanted to give a more kind of readable name to a function, so say we have a set resolution function, sorry, a more readable name to the variables, right? We could then say resolution R, and that would be equivalent to saying int R, but we're creating a new type name. So it's typedef, and then an actual valid type that already exists, and then a name for that type. And that just allows you to do things like that. I mean, most people wouldn't do it in the case of like an int, because that would probably be just more confusing and more misleading to the programmer. They'd have to try and work out what this actually is. Go and find the definition. But for structures, it pretty much always makes sense. So what we would do in the case of a structure, instead of writing our struct, the name of our struct, and then the structure declaration, Typedef struct, and then we don't actually provide any name at all at this point. And so if you think about it, this is the first argument to type, this is the operator typedef. The second argument is going to be the struct keyword, and then actually our struct. So if we then have our struct in here, so it was unsigned, wow, seems I can't type today, unsigned jar R, unsigned jar G, unsigned jar B. So we do the same as we did before. We close off our brace, and so you've got the operator there, typedef, the second argument, which is the type, and we've just declared essentially a new type, struct, which is this struct, and then we give it a name. So then we can say pixel, and then put our semicolon. And then what we've done now is we've created a new type called pixel, which is this struct definition. This then allows us to write a function definition for set background, if we use the same one, where we have void set bg, and we can just put pixel p, because pixel is a new type, and that's more readable than having to put struct pixel everywhere. It becomes really annoying, trust me, if you keep having to put struct everywhere. So I always typedef the struct whenever I use a struct. And it's also just a lot easier then to do things like create a pointer for a pixel, because you would just do, say, pixel p, and then you'd know that was a pointer to a pixel. Whereas when you do it the other way, it's just a bit more unreadable. Alright, let's have a look at some examples of that. So we've got a program here called Hello Structures, and what we're going to do is we're going to start with just doing a normal struct definition. So we're going to say struct pixel, and we said it's an unsigned char R and G and B, and then we can declare a variable, so maybe struct pixel P, and by the way, what you can do is actually assign the values like this if you want. So as long as they're the correct type, they will be assigned to the contents of the structure. Or alternatively, we can say p.r equals 0, p.g, okay, we said that was 255, p.b equals 0. Now, if we have a function then, so set bg or whatever, because we're not actually setting the bg, so let's just say print pixel. Then we can say struct pixel p, and then print out, these are unsigned, so we can say p.r, p.g, p.b, and that's all it's going to do. And then we can call that function print pixel with p. So if we just compile that, yeah, okay. So the problem here is, because we're using struct pixel p and we've only declared it here, we can't see it. So we need to put this somewhere else. We're going to put it outside main, and we're going to put it above there so that it has essentially global scope. It can be seen by everything in this file. Now we'll recompile it. We've got no problems. So I guess it's probably worth starting to think about the scope. So whenever we're using things like this, they need to be visible by everything that's using them. So what we're doing is we declared our structure here. We've created a pixel structure, populated it with values, and printing it via this function. So let's run that and see what it does. And of course it just prints out the values. And just to show you, if I print out this P, so obviously we're referring to this one, just to show you that this is passing a value in. If I change this, so P.R becomes 128, and I'll show you that it's obviously changed there, but you know that. So we're going to print this out the first time, and it will be the value that we passed in. We've changed it to 128. We'll print it out just to show that it's changed, and then we're going to print it out after we return from the function. So there's the original value, there's the value after we changed it, and there's the value after the function. So the value after the function is the same as the value before the function, because as I said, this is just a copy of the entire structure. So all this entire structure, these three contiguous values in memory, so that will be probably unsigned char is 1 byte, so it's going to be 3 bytes, unless there's extra bytes for some kind of alignment, which can happen. So that will be 3 bytes essentially passed into this structure and passed into this function. And no matter how big your structure is, the whole size of it will be copied in. If it's 1,000 bytes, if it's 100,000 bytes long for some bizarre reason, it could be, right? Then, because you can put arrays in there, static arrays and so on, then the whole thing will be copied and copied onto the stack at runtime when you call your function. So when you start having large structures, then it just makes sense to use pointers to them. And we'll talk about that in a sec. So we can actually look at the size of our structure. So we could say size of P, and then we need to say size of struct pixel. And again, you can see how using struct everywhere is just kind of annoying rather than using a Typedef. Yeah, fair enough. So size of is an unsigned long, which is true. It's a bit over the top. I mean, imagine how big your structure would have to be to use an unsigned long, but I guess it can actually happen. Yeah. LU is unsigned long. There we go. Right, let's run it. And there we go. So size of P is 3 bytes, which is what we said, and we know it's going to be 3 bytes because it's RGB. We'll just kind of wreck our program a bit just to illustrate this. If we were to add in a char array called A that had 1,024 bytes recompiled, then the size of P is now 1,027. So it's 1,024 plus our 3 bytes. So you could have very large structures, and the whole thing will be passed into a function when you pass it like that. I'm just going to create a new file called hello Typedef and edit my make file. So I've got a hello Typedef just because I want it to be in a separate file. So let's do the same, but this time we're going to use a Typedef. So to use a Typedef, we just say Typedef. Now what you can do this. So we could do Typedef pixel struct, and then the same as we did before, which is obviously creating a new struct. Sorry, not Typedef. We could do this, right? Create a structure called pixel struct. And then we could do the Typedef. So we could say Typedef struct pixel struct pixel. So type, we're saying create new type. The type we want to give a name to is this, and we're giving it the name pixel. We could do that, and that will be valid. Sometimes it makes sense to do that. I don't really see the point. I think actually you may as well just do this. I think this is clearer. Just do typedef. Don't even give the structure a name. So we just say typedef struct, and then at the end we provide the name. Then we can say pixel p. And you can see that it's kind of, now it's even getting more readable. And now we can define our function. So we say void print pixel, and we just pass in pixel p. And I hope you can see that this is just more readable to do it like this. And it was u p.r, p.g, p.b, and we'll just call that. Yep, okay. Same mistake again. This obviously has to be in scope. So we've got to declare it up here so that we know what a pixel is at this point. Okay, I tell you what, let me just put that back because I think I've just moved that without really showing you what the error says. So error unknown type name pixel. That's because at this point on line 3 it doesn't know what a pixel is because we've declared it here. Okay, so I'll put that back. Now let's run it. And of course it just prints out our pixel type. And we can then even say when we did size of and we had to say struct, we can say size of p, well, the size of our type really, the size of pixel. And it was an unsigned long, and we just say size of pixel. So put that one on the new line. Missed out a bracket there. And a pixel is still 3 bytes, of course.
So you've just seen there that you can use the size of operator to get the size of a structure, and you can pass in the typedef name to the size of operator. Getting the size of a structure is really useful when we want to use pointers to structures. Now, of course, what we could do is we might have a pixel p here, and we can obviously take the address of p and pass that into a function if we want. So let's imagine that we've got our function, and our function is just going to be void redder. It's going to try and make the pixel redder, and it takes a pixel pointer as an argument. If we want to refer to the members of the structure when we pass in a pointer, we don't use the dot notation. We use this, which is essentially a dereferencing operator. So we do p arrow r, and then if we wanted to change the value of red, we can say plus plus to increment it, for example. Or I'll tell you what, let's be a bit more explicit than that, or clearer. We're just going to change the red value to 255. Otherwise, we're going to overflow if we add 1 to 255. So that would be how you assign a value to the member of a structure or a variable within a structure when we're passing a pointer to it.
So I'm not going to make the same mistake again. Obviously, the type definition for our structure needs to be up here in the declaration of our structure. It needs to be here, so it's typedef struct, and then we said it's 3 unsigned chart, and we gave it a name pixel. What we're going to do is have our function redder, or let's say make redder,
and it takes a pointer to a pixel P, and it sets PR to 255. Let's just check that that actually works then. And we'll do this first just by locally declaring a pixel value called P again. And we can give it the values. So that's the red value is going to be 0, and 255 and 0. Now when we call make redder, we can pass in the address to P. And let's just print out the pixel before and after. To see whether or not we've actually changed it. There it is before. Of course the red value is 0, green is 255 and 0. After we've called the function redder, we've now actually changed it. So that's how you refer to the member of a pointer. So I just want to quickly show you what happens if you were to dereference this pointer. What would you actually get? Well, we would take, so say we were to do something like this, pixel q equals, and then we dereference p. Well, if you remember, when we dereference ordinary variables, we just get their value back. And it's the same here. We've just got the value of the pixel p back. So all those 3 bytes, that is its value. And they're going to be copied into the local variable q. So if we then do something like q.r equals 255, compile that and run it, we can see that we have not changed the red value. That's because this is, when we dereference, we're getting a copy of the value. So we need to use this notation so that we're referencing the actual value that we've passed in. We're dereferencing the address there, and we're dereferencing that particular value. So we're saying, go to this address, go to the element R within that structure and change its value to 255.
What we can also do is work with arrays of a structure. And so to do that, if we wanted 10 pixels, and maybe that's our screen, it's a very small screen, so 1,000 pixels, still very small, but in any case, we could do something like this. So we'd say type is pixel, so pixel, and then it's going to be, our variable is going to be called screen equals malloc. We'll just put this on a new line. 1,000 times size of pixel. And then that's going to declare space or declare memory for 1,000 pixels. And we've got a pointer to them. This is just like any other array. We can then say screen 25 to modify the 26th element of the array. And if we want to change the red component, we do not use the arrow, because the arrow only operates directly on pointers, whereas if you remember from the pointers tutorial, when we use brackets like this, we're actually dereferencing the pointer screen. We're going to the address 25, element 25, so that's going to be 25 times the size of this, which is 3 bytes. And then we're actually operating on the value of that object, and the value of that object there, and the type of that element there, is a struct pixel type. So we use the dot notation, and we could change then the red component of the element at index 25 by using the dot notation like that. So just be aware then, when you're referencing an array, you've got to use the dot notation in that case, because we're dereferencing it, and then our type is a pixel structure. Whereas here we've got a pixel pointer, so we're using the arrow. If you get it wrong, if you tried to use the arrow type here, you would get an error message. So you would know that it's wrong, and it would tell you
that it's wrong. Let's take a look at that. And what we can then also do is we could have a whole bunch of these pixels, and we could call that the screen. So we could say a pixel pointer called screen, and it's going to be an array of these things, and we're going to dynamically allocate them 10 times size of pixels, so there's 10 pixels there. What we could then do is we could set their values and say screen I. So we don't use the arrow notation here, and the reason we don't use that is because when we index into screen, we're now pointing at the value, and the value is a pixel struct. So we then change it like this. So if we use an array into it, then we're going to change it like this. If we're operating directly on the pointer, because obviously this is now dereferenced essentially by doing this. Whereas if we're operating directly on the pointer like we are here, we use this arrow. But because we've already dereferenced it, now we use the dot notation still. So we could set them all to 0 to begin with, and then we can define a function called make screen redder, and takes screen s and our length of our array. And all this is going to do is go through each of the pixels and change the red component to 255. And what we can do is we can say we can print out what this looks like before. If we just go through and we just print out the component, or the red component, then we call our make screen redder function, pass in our screen and our length, and then we're just going to, oh yeah, we need a new line, and then we're just going to print out what it looks like after, and we're just printing the red component. So let's check that at work. Oh yeah. What's the problem here? Unknown type name screen. Oh yeah, of course. It's a pixel type. So here we are. Before, the red values are all 0. After, the red values are all 255. So we can pass in an array of pixels and modify them like that. An array of any kind of structure type, and that will work. And that's really about it for structures. You've seen how to create them, how to create pointers to them, and how to pass them in and out of functions, and how you can change them within a function. A couple of other notes, I guess. Giving it a name like pixel is probably okay if you've got a small program. If you're using external libraries, you might end up conflicting with a name that's already used, in which case you might want to prefix any of your structures names with the name of your library, whatever that is, to avoid namespace clashes. Now in a structure you can use any type you like. You can fill it with as many types as you want, and you can also use other structures within structures. This becomes very useful for hierarchically constructing kind of objects. So if we look at something like C++ or Java, they have the concept of an object, where your object might be a car or whatever. And I'll just mention this. So your object might be like a car, and they would use, there's some kind of syntactic help on how to manipulate the car. So say we wanted to start the car, like perhaps it's a simulation of a car or something like that, then they could do something like car.start and actually call functions that would then operate on that car object. In C we can't do that, not easily anyway. You could probably do it in a really weird way, but what we have to do then is we have to pass our structure car into a function. So we would have a function, for example, called car_start, and then we would pass our car into it. And that's always the case. So that's the main distinction between using objects and using structures. despite some kind of minor control over encapsulation and what's visible, that I believe is almost meaningless, because if you've got the source code you can change everything anyway. But this is really the only difference. In C++ and object-driven languages, you'll have the structure or the object here, and then you call functions upon it. But it's essentially just doing this. It's as if you defined a function called car start and you're passing in the car. And if you had like car dot, I don't know, set color, use the American version of color, and then we had a pixel P, you might do that in your object kind of oriented language, and it's called object oriented because it's oriented towards the object, you're operating on the object. Whereas in C you'd have to do something like car set color, you'd then pass in the car, and then you'd pass in your pixel, right? So the object essentially becomes always the first argument of your function. But that is pretty much the only difference, besides some other things like constructors and so on. Probably when we finish this, or at least got quite far in the C tutorial, I'll show you just how you can very easily actually start using C++. So to finish this off on the idea of structures, I said you can nest structures. So that's going to be the exercise to create a screen object or screen structure. Now when I talk about objects, I just call structures objects sometimes, because semantically that's kind of what they are. So if I say a screen object, then obviously in C we have to implement that using structures, but semantically it is an object. So what I want you to do for the exercise is create a screen object that has a width and a height, and within it then has a pixel array, just to show that you can do nested structures. We're going to end now, and I'm just going to end with the solution to that. But otherwise, thank you for watching, and I'll see you next time. So we're going to have we need a screen type and a pixel type. Because we need to know what pixel is before we use it, we're going to define our pixel type first. So we're using a Typedef struct, and then the struct, and it's called a pixel, and it has, same as before, unsigned char RGB. Now that we've defined a pixel, we can actually use it, and we're going to create a new structure, which is going to be our screen. And our screen is going to consist of a width, height, and then it's going to have the array of pixels. So we're going to have a pixel data. So the actual data of the screen we'll call, for example. Now, normally what I do is, so if I wanted to create a new screen, typically I would create a function to create that. So I would have a function that returns a screen pointer, and it would be called screen new. And this is kind of making it a bit more in line with object-oriented languages. We probably need some parameters if we create a new screen. We need the width, we need the height, and at the moment this is just going to create the data, but it's not going to fill it in. And what we would then do is we can say screen s equals malloc. We're using malloc, so we need standard lib, and then it's going to be just size of screen, so it's just 1. Now, and we're going to return that at the end. We're going to now set screen width equal to width. We're going to set the screen height equal to height. And of course we need the data. So the data is going to be malloc width times height times size of pixel.
So that will create that many pixels, and that's the data for our screen. Now typically what I will do is, if I create something to essentially create an object, I will also create a function to destroy the object. So I could have screen free, for example. Obviously it needs to take a pointer to a screen, and then there's a couple of things we need to do there. We first of all need to free the data, because that was allocated, and then we need to free the pointer s itself. And that's pretty much it really. I mean, you've seen how to nest the structure. We'll create one more function called screen print. It's going to be void, and it takes a screen object. And now, because all the stuff is encapsulated inside our screen object, we can say I is less than screen width, or actually height, for j equals 0, j is less than screen width, and we will just print out the element. And of course, each one is going to be an RGB element. So it's S. We need to do a bit of jiggery pokery here to get the actual index, and just to be kind of explicit, I'll put the index equals I times S width. So it's the row times the width plus J. So, and then we would say S data index dot R G and B. I'm just going to print that out. At the end of each row, we're going to print a new line. And we're just going to do that. They've got no real useful values at the moment, but who cares? Or maybe we do care. Tell you what, let's just give them some values then. Why not? Just copy this stuff. We need the index again. We'll make them all. This is going to be equal to I, the red component. That's going to be equal to J, and that's going to be 0. And then in our main function, we're going to say screen s equals screen new, and it's going to be a 5 by 5 screen. At the end, we're going to do our screen free, and we're going to do screen print s. That's what we're going to. That's all we're going to do. Let's compile that. What's the problem here? Yep, print is not a valid function. It's printf. Right, everything's fine. Let's run that, and here is our 5 by 5. Let me make this a little bit bigger. Here's our 5 by 5 screen, and we said that when we actually set the data here, we said that the red is equal to I, so the red is essentially equal to the row, and you can see that there, whereas the green is equal to the column, and the blue is 0. So there you go, that's nested structures. I hope that was useful, and I will see you next time.